Distinguished guests, ladies and gentlemen, greetings once again, and welcome to the Korea AI Summit 2024. And please allow me to introduce myself once again. My name is Seojin Jessica Park, and it's my great honor to be hosting this meaningful conference. And as previously mentioned, the Korea AI Summit 2024 is being broadcast on our official YouTube channel. And I am very delighted to be joined by both online and offline participants as we can have more productive and engaging discussions with more participants around the world. All right, now, without further ado, let us hear from our first keynote speaker. And for that, please allow me to introduce Professor Klaus Robert Müller from TU Berlin. He is a full professor and chair of Machine Learning Group at the Technical University of Berlin and a director of the Berlin Institute for Foundations of Learning and Data. And he'll be sharing his insights on AI for the science. And for that, please welcome Professor Klaus Robert Müller with a big round of applause.
All right. Hello, everyone. It's a great pleasure to be here, and thank you very much to the organizers for having me. Today I will talk about AI for the sciences and just focus on two particular parts. So I will discuss history of science, and I will also discuss machine learning for quantum chemistry. For both, a key ingredient will be the use of explainable AI. So let's start with explainable AI. I think we all know if we are using models to predict things, these models, the deep networks, they are complex, and some people, say they are black boxes. They complain about it, and so, of course, this was true for some while, but it's not anymore. So some of the, since maybe 2015 or slightly before, people have started to work on using methods to shed light into the black boxes. And I would like to show you a bit about how this could work. So, assume that we have here a full-blown computer vision model, a deep model, and this model sees a new data point, which, obviously is a rooster, and the model has been, well trained in distinguishing roosters from buses and, poodles and God knows what. And then it says it's a rooster, and you wonder why on earth does this model say this is a rooster? How does it do that? What is the background behind the decision making? And for this, basically, you have to put the model upside down. It's a nonlinear function, and you need to sort of invert this nonlinear function, which is a hard math problem. And there's a number of people who have been tackling this problem, and I will be using the layer-wise relevance propagation algorithm that we have been proposing in 2015. But this has become an own community. I think they had the Second World Congress on explainable AI recently. So assume that you're applying the XAI magic, and for this particular case, you see in a heat map that certain pixels in the input space are more relevant to the decision making. And so you can see it's essentially, the red points that matter, the green points the model is neutral to. So here you see it's basically the rooster's comb that is relevant for the decision making. So this is just one example of, a situation where we can, understand what the deep learning model has done. Other examples I will refrain, but I will use the technique in order to double check whether the results that we get in the sciences are meaningful. Because otherwise we have a prediction of something, but we don't know whether this prediction makes sense in the sense of physics or the other disciplines. So I will start out with AI meeting the history of science. I have chosen this because it's very unusual as an AI application. And it's a paper that just recently appeared, and it is the XAI part is based on this PAMI paper that is already a bit older. Let me give you a bit of a background of why this is interesting and what we are looking at. So basically, one question that history of science has is how did ideas come about and how were they spread during time and space? And so this is something that we will look at. And since yesterday at dinner, I learned that there are some talks about astronomy as well. So this is also interestingly data that has been collected from astronomy books of a certain period in time, namely 1486 until 1647. This actually, from the historical point of view, has been a very interesting time because this was the time of the mathematization of the sciences. And so the most early algorithms in the sciences have been algorithms where people that were cast into tables, and from these tables people could read off things. Let me give you an example. So back in the days, you would let me show you this picture first. You see this is the position of the sun in the zodiac sign from one of these old books. And back in the days, people were writing some stories about what has happened at a certain point in time, saying that the sun was standing in a certain position in the zodiac, and then there was a certain planetary configuration, but there was no date, right? And so one guy, Melanchthon, a philosopher from Germany, he said, we can only understand our cultural identities if we can put things, in a time sequence. So because then we know what comes first and then what comes next and how the historic developments are. And therefore, it was very important for people to actually translate, what was in the old stories and reports into, dating them, okay? So here you can see some of the tables that are in these historical books. And you can see that these are from different times. This is 16th century, this is newer, and this is more older, right? And so we're not talking only about historical documents of that time, but we are also, so this idea of translating, solar positions into time was already, in ancient times. So that has been applied only. Okay, so these are the tables, and so basically we have a corpus, which is the Sphera corpus, which was collected by the Max Planck Institute for the History of Science, and this is a collaboration that we as Bifold had with them, and in particular Matteo Valeriani, and so you would have certain books, astronomy books, that explain astronomy to the youth of this period in Europe at different centers of cultural activity. And so sometimes they invented a new algorithm, and this was progressing through space and time. And, the corpus that we have is about 78,000 pages, and the tables, they are quite a mess. These are, printed tables from wood prints in the beginning. And so they were changed and rearranged, and the layout was changed, new columns were added, and so on and so forth. So the standard computer vision tools wouldn't do with that kind of data scarcity, I would say. And one aspect for historians would be they would need to understand what is similar, and you could understand what is similar by comparing tables, right? So if you want to compare tables in this extensive period of time of 200-something years, then you would have to compare something like 78,000 pages with tables, times 78,000 minus 1. And that's, of course, a lot of work. And if you're a well-trained historian, you can do this rather quickly, which means that you can compare a couple of tables per day. But it would take hundreds of historians centuries to, even get close to saying what is similar to what. Okay, so we trained a neural network to compare objects, to compare similarities, and then we would explain what this neural network, why is it saying that something is similar to something else in terms of explanation. And you can see, why is this table similar to this one? And you can see that there's a certain combination of numbers and parts in the column and so on and so forth. So what our similarities that were learned could be, looked at and, put under, serious control by historians. So, first step, we have all these pages. Second step is we train a similarity model. Then we have the similarities, and then we can start clustering spatially and temporally. So let me just give you a remark why this is special. So usually historians, they look at documents of a certain time and a certain place, and they dig deep. But this is the first time that we have been looking at, 2 centuries across Europe, taking into account all kinds of documents. So here's again tables and the zodiac position. This was one aspect of the mathematization. The other part was climate zones. Okay, so after our exercise, we now have similarities across documents, across time, and across places. And we can start studying who influenced whom, when, and how, which is, I think, an interesting question in the how to understand the ideas in science emerging. And I will show you just a brief video. Okay, so here you see a map of Europe, and there's different documents influencing each other. So you can see Paris. So this is now about the concept of climate zones spreading over Europe in a certain time. So Paris, Cologne, Leipzig, Venice, Avignon, Seville, and Lisbon. And here's a very interesting, slightly unexpected place that you may not know so well. That's Wittenberg. Wittenberg is the birthplace of book print. And one of the interesting points was it was also, where the whole world was Catholic, but this was the the root point of Protestant religion, which made it very open-minded to the sciences and mathematics. So you could see, the spatial and temporal evolution of knowledge across Europe of that time. So there's a lot to be said and about the insights that people didn't have before, that you can read up in our Science Advance paper. So let me move to another topic of the sciences. I've been, using machine learning in the sciences for quite a while, and one of my pet projects was always to use machine learning in physics. And let me just give you a bit about the background there. So what we like to do is we'd like to predict quantum mechanical properties across chemical compound space. So let me tell you a bit about the story there. In 2011, there was a program at IPAM, and I was invited there. I spent my sabbatical there. IPAM is Institute for Pure and Applied Mathematics at UCLA. And so people were discussing how to compute the quantum properties of matter. And the one equation that is governing this is the Schrödinger equation. And here's Schrödinger. It looks suspiciously simple, but it's actually very complicated if there are more than one electron. So for the hydrogen atom, we can compute this in closed form. For anything else, we have to make an approximation. These approximations were very successful, and they got the Nobel Prize because one of the approximation, density functional theory, was actually very successful in solving many problems that chemists had when computing quantum properties. The problem there is, however, that despite this approximation, it's still, computationally highly intense, and supercomputers are still used, approximately half-half by the climate people and the quantum chemists. So what I suggested then was to say, how about not solving the equation by making an approximation and then solving these approximations, but otherwise just generate a lot of data from the Schrödinger equation. So you generate a number of molecules and their chemical properties, quantum properties, and then you use a machine learning model to basically predict this context. So in a way, we're not solving equation, we're predicting the outcome of an equation, right? Which was very heretic at that time, and it still is. And the interesting thing is that this actually worked. And so, in standard DFT method, you have about 3 to 5 hours per molecule or 4 hours for material in terms of compute. Or if you go a bit beyond in terms of precision, then you can easily spend 7 days on the with one single data point, one molecule. But if you have a machine learning model that is well trained and that makes this prediction, then it's spans of the order 0.1 millisecond in order to make an accurate prediction. So even out of sample. So that's about 30 million times faster. And that was a huge step forward. And with that, one of the dreams of this community started to become accessible. Namely, in astronomy, we know that, navigating this planet, maps of, astronomical maps have been, essential. And so if we think about having a map of the chemical space, this would be extremely helpful to navigate this space and to go from, one molecule to the other and understand about what is similar in terms of properties. So just to make this point, there are more small molecules than atoms in this universe. So it's a huge and vast space. Even with 0.1 milliseconds, it's impossible to navigate it, but you can still navigate some places, right? Okay, so let's switch gears a bit and let's talk about molecular dynamics. So previously, in what I was talking about, I was saying, well, we are navigating chemical space, meaning we are taking one molecule and predicting a quantum property. Now we are taking one molecule, and then this molecule can start to dance, right? So that's called molecular dynamics. So at finite temperature, the molecule will move around. And it will move around according to the quantum properties, right? So again, the same as I said before holds also for the quantum properties of molecular dynamics. So from the machine learning point of view, assume that you have 5 atoms, okay? Then each of these atoms lives in a 3D space. So you have 5 times 3 coordinates. And for every 15-dimensional point, meaning a molecular configuration, you have one energy, forces, whatever, right? And some quantum properties. So in principle, you can sample this space and then compute the energy surface, and the derivative of this energy surface will give you the molecular dynamics. It will show you what are the forces, quantum mechanical accurate forces, that will move, the molecule from one configuration to the next. So it's basically a regression problem. But for something like aspirin, which is not very large, you will need to sample about 50,000 points times 5 hours, by the way. So just to make this point. It was absolutely essential to bring in physics knowledge, prior knowledge, to solve this problem more efficiently. For example, for aspirin, if we are accepting that energy conservation holds in this universe, and we're putting this into the models, and that certain symmetries are given, then we don't need to sample 50,000 data points, but only 50. The solution will be formally equivalent. And that's a huge difference in terms of compute. Now we are going one step beyond that and saying, how about simulating large molecules? So let's tell you about the impossibility of this endeavor in a brute force way. So assume that we have a system of 100 atoms, and we proceed as I explained. So we are sampling the energy surface, and then we have enough points to make a regression, and then we have all the forces essentially, and we build a model for this, a machine-learned force field. Then we take about 4 weeks of compute for that, okay? Now, assume that we want to do this for a larger molecule, say a protein. So something with, say, 10,000 atoms. So then the algorithms, the quantum algorithms with which we can compute quantum properties like DFT, they scale like n to the 3 or n to the 5. So which means that, for a 10,000 atom system, we would have to do 10 to the 5 times 4 weeks of compute, which is basically age of the universe, whether it's expanding or not, right? So, so the question is then, can we somehow deal with this? And what we said is, how about splitting this large protein up, fragmenting it, and then, like in a patchwork blanket, stitching it up together, which would be one part of the solution. So you have a bunch of local force fields that you put together. But the problem is that physics works with long-range correlations. So you only have local models. That means you don't have long-range correlations. So our life wouldn't exist if we wouldn't have these long-range correlations. So van der Waals interactions, they are very, very weak interactions, but still they make proteins fold. So this means that if we are not taking into account of the long-range interaction, this whole exercise is futile. So we needed to not only stitch things together, but we needed to actually also learn about long-range stuff. So what we did was we put a new transformer architecture, which was the first transformer in that field. We put a lot of physics knowledge, and then we put a lot of CPU hours into fragments, and then we had a model. So this was this paper. And so the idea is basically we had very small fragments or slightly larger fragments. So we call them top-down fragments and bottom-up fragments. And then we have this transformer that tries to put things together, stitch things up, and get the long-range correlations that are somehow reflected in the larger fragments. So that was the idea, and it actually worked. So how did we get the fragments? First, it's a bit boring to do proteins without water or molecules without solution. So we always put the stuff into water. So the red stuff is water molecules. So then you have the molecule and the water molecules around it. And then, you would cut such a sphere, and then you would saturate the bonds, and then you would compute these fragments. That would be the top-down fragments. And then, you have your force field implemented in the form of a transformer, SpookyNet, and then you can start playing with it. And you can, for example, take this alanine 15 leucine, which, as we know, folds, right? So we can look at it, and then first stretch it, and then stretching it means that we are starting at some point on our potential energy surface, and then we follow the gradient, right? And do the molecular dynamics. So this is what happens. So this is a full quantum simulation of this object, and you can see how this folds. And you can also analyze this. So we know from AlphaFold that you can predict the folded state. But I'm showing you, so to say, what happens between the beginning and the end, right? And so here, for the connoisseurs of you, this folds into an alpha helical structure. That is known. But it also fluctuates to a 310 helical structure. This has been, occasionally observed by experimentalists, but not, the classical force fields won't give this solution. So this actually is a true reflection of what happens. In fact, this molecule is constantly fluctuating between 310 and alpha helical structures, something that we could observe for the first time, okay, in theory. So that's quite interesting. It tells us basically that, what people, Karplus and others, already knew back in the days in their classical force fields that were not quantum mechanically accurate, that there's a lot of wobbliness in these large molecules, amazing wobbliness, and that's an intrinsic part of their properties. And if you now look at a larger molecule, for example, the receptor binding domain of the spike protein that has been bothering us through corona, because that has been binding to the ACE2 receptor. If we look at that, it's not like you take the protein and you just shove it into a garage. It's rather there's a dynamical process. So the protein rather makes a dance on this receptor. It's more like samba. It's 6 to 10 hydrogen bonds that are on and off all the time. And that makes this very strong binding. Okay, so this is now just you saw that slide already. So this is comparison between the classical force fields and the new method, which is quantum mechanically accurate. It has an accuracy of 1 kcal per mole approximately, whereas the classical force field is around 50. So we can understand the folding dynamics, and we can also see in larger molecules, for example, here the chrombene, we can see structural fluctuations that you cannot see otherwise in classical force fields, which is, I think, interesting. We can now derive spectra from this and compare them with the experiment. And you can see that, here's the terahertz spectroscopy experiment where we can see that the new model is pretty good given possible similarities in a biological molecule. And of course, we can then make further progress and start studying other architectures. I was talking about the transformer architecture. One thing that nowadays people in quantum chemistry often use is equivariant methods. The problem, and so this is now also quite new from this year, this is now an equivariant method that is fast. So usually the equivariant methods, they are sometimes a factor of 1,000 slower than the ConvNet. And the Socrates architecture, which I don't expect you to appreciate in this slide, but it's basically an interesting trick to make an equivariant model much, much faster, similar to like a standard ConvNet. And that makes a huge difference. And so if we are looking at the scaling, then we can see that these other methods are typically scaling like to the 6th power, whereas we are at squared, which is kind of a nice thing. L denotes how many spherical harmonics we are using. And so if we are looking at the number of the quality of our prediction, so low is good, so that's the number of the mean absolute error, and that's the number of frames per second that we can compute. So this is a very sweet spot. So we are fast and accurate. And you can see that here, for example, also the convolutive models are fast but not so accurate, and so on and so forth. So it's a sweet spot in this domain. And for that, we can now apply this to larger systems, also like the buckyball catcher and some nano systems. And there was last year a very interesting community workshop where people were invited. So it was like a hackathon or data competition where people would bring their models and would make predictions across a variety of applications. And so Socrates was doing well in that competition. And so it's fast and accurate. And now we can say, well, how about taking this and going one step further? Okay, because we have now a very well-performing architecture and it's fast. So how about putting this into a foundation model? Okay. So we are, remember, in the beginning, we were dreaming about chemical spaces and navigating across it. Then we said, okay, for one molecule, we can do molecular dynamics. We can do it fast. We can do it accurate. We can even do it with larger systems. But how about now in a foundation model, we would say, okay, let's generalize across chemistry. And that's, of course, a very hard task. And here's, the kind of system that we built up. It's currently under review. So we basically have something like 4 million reference data points. And then we predict all sorts of things and compute Hirschfeld ratios, partial charges, get the electrostatics right, the dispersion, and so on and so forth, and use all that to predict forces. But we're not doing this only for proteins or just small molecules, but we are doing this also for water, proteins, glycoproteins, lipids, then nucleic acid, carbohydrates, and so on and so forth. So that's a an interesting part of chemical space. It's not all of chemical space. There's more, but there's something that we could start with. And so the interesting point and lesson learned is that this model, that because it's based on Socrates, so we call it SOLAR. SOLAR is very close to what I would call a universal force field. So we can apply it to some new compound and do molecular dynamics, and it will be reasonably accurate. So let me say what is reasonably. So if we are taking some data for a new molecule and we're generating this data and we're training a dedicated model, then we will be better, right? But not much, right? So this foundation model is able to give a very nice force field, but not the best in all disciplines. But it's a good basis from which we can fine-tune, for example. But even taking this model out of the box was astonishingly useful across all these chemical scenarios, which honestly was a bit surprising for me. So it means that this foundation model has understood a bit of chemistry and about how to represent chemical bonds and molecular structures well. So that was one thing, and there's also some limits that we saw. And I think that clearly, we have to acknowledge these limits. And right now, the model has taken data that is available, across the internet, and it has been generated with different codes, which means that it's not totally compatible. So there's that aspect that is common to foundation models. So I think we can do much more if we don't have this issue. So let me conclude. So XAI is important for understanding, gaining insights. It's in the historical case, and also for the molecular applications that we were talking about, it was important to double check whether this is really doing physics. Then these architectures that are introduced, they learn to represent a chemical environment, similarly to learning to represent language, as in large language models. Using physical priors is super important, and we are allowed to reduce the number of data by orders of magnitude. And there's a lot of open questions, and I thank you very much for your attention.
Thank you very much, Professor. Thank you. Thank you very much once again. And he talked about the convergence or utilizing AI technologies such as algorithms or machine learning in chemical species and physics models. Once again, thank you very much. And while listening to his lecture, I had to really concentrate in order to understand. And I'm sure that there must be some of you have questions like me. So if you have any question, I think we'll be able to receive one question from the floor. So if you have any question, please raise your hand. We'll deliver a microphone to you. Any question? Yes.
Yeah, thanks for the great talk, David Lindell, University of Toronto. So I wonder, we've been working on recovering maps of the 3D electrostatic potential from cryo-electron microscopy.
Mm-hmm.
I wonder if this new method, what we're trying to do is, you can recover different conformational states, but you can't know how the particle moves between them. Mm-hmm. So I'm wondering if, combining what we get out of cryo-EM with these methods would allow us to do that.
That's a very great question. So in the Socrates paper, we had one application which we used to showcase, the properties that you can explore with a fast model. And in one of the, showcases was really, exploring the conformational spaces. So that's a very hard problem, and it needs to be done very precisely quantum mechanically, because the conformational differences are so small that you really have to have a good level of quantum mechanical theory. So I think it could be done.
Thank you.
And just as a remark, this is not yet even submitted, but we have been having a very nice collaboration with a scanning probe microscopist in Jülich, because they and the question. So what they do is they have they use a tip of the scanning probe microscope to lift up molecules and to do molecular Lego, right? The problem is, if you want to understand how things look, right, then you need your tip, or you need a model or you need a second tip which is not existing, or you need a model which is a quantum mechanical model of what is happening. And there we were also making attempts to look at all the configurations and the conformations, in fact. Thank you.
Thanks. Very interesting.
Thank you. I hope it answered your question. Now we will wrap up there due to time constraints. But once again, thank you very much, Professor Müller, for your insights. Let us give him a warm round of applause once again.